name is Keiichi Yamada. I came from Osaka, Japan. Usually, at the top, this is called the infuser, infusing the drugs into the epidural space. And drug is filled in an elastic balloon. The elastic balloon gives us a contractive force. So it pushes out drugs. And there's a capillary at the end. And depending on the size of the capillary, we can control the flow rate coming out from the drugs. But as you see at the bottom, the red curve corresponds to the flow rate of the infuser. It starts from very high flow rate, goes down, and then finally goes up and goes down. So the flow rate is not constant. What we want is the always constant flow rate driving machine. If I use the ambulatory pump, which I have shown at the previous picture, shows the flow rate is just a green line. It's pulsating. This isn't good. So we have been looking for some mechanism which can give us almost continuous flow rate from the beginning to the end of the infusion. Okay. This is the micropump we have created in Japan. This is a metal micropump. At the bottom, you can see a cross-section of the micropump. And the gray part is made of stainless steel, and the yellow part is called piezo, as you know very well. And there is an inlet valve and outlet valve at the bottom. It's very small and it's very tiny. This itself is just a pump. It doesn't have any gear, any battery, and no motor. It's very, very compact. Everybody knows how it operates. When you apply an electric field to piezo, it changes the shape. And if I apply an electric field from bottom to the top, the yellow part, which is piezo extends in a radial direction. Then the piezo sticks to the diaphragm, which is made of stainless steel, which does not expand. As a result, it can have a convex shape like this. It can suck the drugs into the pump chamber. And if we apply an electric field from top to the bottom, I mean that I apply a positive voltage, the piezo now shrinks. Then the pump has a concave shape, and it pushes out drugs. And energy consumption is only 20 milliwatts. It means that these devices can be operated for a long time with a very, very small amount of energy. It's really nice things. And at the bottom, I show that there is some volume called the stroke volume, which is subtended by the upper region and the lower region of the diaphragm. Now, the flow rate can be calculated by the stroke volume multiplied by the frequency. Frequency means how many times you give a push out drugs per second. And this is the way how to make a piezo metal pumps. We use the diffusion bonding machine. We piled 8 or 12 sheets of stainless steel, each of which has a different pattern of a punched hole. And to glue it, we piled it into a thermal diffusion bonding machine. We applied heat and pressure. Then after making the solid body of a micropump, we can just put a glued piezo on top of it. So that's the way of making a micropump. It's very easy to make it. It's been almost 10 years since we started to do research about micropump. We struggled a lot. And here I have shown some problems we overcome. And some of this has lost a lot of weight to solve these problems. First of all, we used micropump and created a prototype using micropump, which is very tiny, which has a very small display and small keyboards. And we brought this prototype to hospital to get the opinion of nurses and doctors. They complained. They didn't like it because they think that the small keyboards and small display leads to misoperation and misjudgment for medical treatment. They want to make it big, but we didn't want to do it because having a big display and keyboard really spoils the compactness of Micropump itself, and we were in trouble. Then finally, I met one doctor said, nurses are doing very bad, how can I say, they are not concerning about the real treatment of a patient. When we put the display, they keep recording the numbers appears on it. They think that's their job, but the real job is take care of patients, paying attention to the patient. So we finally decided to take out all display and all keyboards from main body of the Micropump system. So this is it. Doesn't have anything, no display and no keyboards, leaving only the warning diode. That's it. This is one of the ways. Also, the one mobile phone, we trusted all programming to the mobile phone. Then we provided the special application to control Micropump. And this one mobile phone can control any number of driver unit where the Micropump is inserted. And you know that the one nurse has to take care of many patients, so they has to visit many sick wards. So by just carrying one mobile phone, they can just check all conditions, they can program all Micropumps. It is very nice, and usually it is very seldom that the nurse or doctor change the program, such as flow rate, possibly once or twice in a week. So it's really stupid for a patient to carry all keyboards and display all the time. And finally, we found out the bad guy was air trapped inside the Micropump. When there is no air, when pump activate, the pump gives maximum pressure to the liquid. And that maximum pressure stays until entire drug is pushed out. That's why flow rate will follow the black line at the bottom. And you can see that the pumping mode is durated about 25 microseconds. Now, if we have air, what's going to happen? On the right, when pump is pushed out drugs, quickly air itself can be compressed. Here I assume the isothermal compression, not adiabatic compression, but just isothermal compression theory tells us the pressure goes to PVA or divided by VA minus VS, where VA is the volume of air and PAT is the atmospheric pressure. It goes up. Then after the air is compressed, the drug goes out. Now there is a space for air to expand, so the pressure goes down. Then flow rate goes down, so it follows the red line. And if we have a very small flow rate like this one, and the pump will be ended before expel entire drugs. So some of the drug will be left inside, which that is corresponding to the shaded area. I call it wasted drugs. So this is so only percentage of drug is expelled, plus only a percentage of stroke volume is filled with drugs. This is the reason why we have so much decrease of flow rate. And there is some other very terrible situation sometimes happens. In this case, drug is trapped inside the proximal region of the outlet valve. Then we have a surface tension. And we have a back pressure. If the inner pressure is smaller than the pressure provided by surface tension plus back pressure, there will be no flow. So if the valve completely sticks to the volume. So that's why we need to have a strong pressure. Now, I don't have such more time. Just I want to talk about the small application, many applications of Micropump. This is the list of drugs injected to a patient during heart surgery. There are so many drugs, and each drug requires different flow rate. So each drug has to be stored in the pumps. Next application is insulin pump. The micropump system is so tiny, and it can be operated with a very small amount of energy. It means we can have a very small battery. We can have an insulin pump, smallest and most inexpensive insulin pumps. Insulin is stored inside. This is my dream. The market size is so big. Okay. This is one example. We have completed already the insulin pumps, and it works well. You will see this when you are diabetes. Okay. Anyway, we have struggled a lot, and even though we have made a lot of good German friends, but now it's time to make money.